Our third target of our chemical reactions unit is learning how to apply the law of conservation of mass in terms of balancing chemical equations. But first, before we start, we need to focus on some basics. A balanced chemical equation shows not only the formulas of substances in a chemical reaction, but also the amounts of those substances. In order for this to work, the formulas of the reactants and products must be written correctly, which is why we had our bonding and nomenclature unit from first semester. And we reviewed it in SC 5.1. We learned how to interpret chemical equations. Numbers are used to balance substances, and these numbers are put in front of symbols and formulas, and they're called coefficients. So the law of conservation of mass applies to balancing chemical equations because the number of atoms of each element on the reactant side will be equal to the number of atoms of each element on the product side. So in order to balance, we have two key rules. The first is that you are never changing the chemical formula or the subscripts for the reactants and products. What's written on the paper are set in stone. What that means for us is that we are not adding random single elements. What we can change, however, are the front numbers, or the coefficients. So what we'll be doing is we're adding sets, or we're adding molecules in order to balance chemical equations. So there's two different ways to approach this. We can use pictures and drawings to balance chemical equations, or we can do it by using an atom count, or what I'll call the math way. So what we're going to do is we're going to look at the same equation from the two different perspectives, and you can decide which pathway works best for you. If we're going to use pictures, here's a process you can take. The first is that you're going to draw one of each molecule and complete an initial atom count. So if I'm looking at Fe2O3, there's no plus signs, and all the letters are touching, which means all of these are bonded together. So I have 2 atoms of Fe, or iron, attached to 3 atoms of oxygen. On the right-hand side of the arrow, so on the product side, I have Fe by itself, and I have O2, which means I have 2 atoms of oxygen bonded together. So to start, I have 2 atoms of Fe on the left and 3 atoms of O on the left. On the product side, I have 1 atom of Fe and 2 atoms of oxygen. So because notes are typically broken down into chunks, what we're going to do is we're going to take a moment and just redraw what we have. And this will make sense in just a second. Pause the video if you need a little bit more time and restart when you're ready to go. So what I can see on the left-hand side is I have 3 atoms of oxygen and 2 atoms of iron. But on the right side I only have 1 atom of iron and 2 atoms of oxygen. So I can add another atom of Fe, and my Fe's are balanced, or they're the same on both sides. But my oxygens are not. So because I have more on the left, that means I have to add oxygen to the product, or the right side. And while it's tempting just to put 1 oxygen there, I can't, because oxygen's only allowed in pairs, because it says O2. But if I add another pair, which is what I'm supposed to do, now I have 1, 2, 3, 4 atoms of oxygen versus the 3 on the left. This is still not balanced. But now I have more on the right side, so I'll have to add oxygen to the left. Again, as tempting as it is just to add 1 atom of oxygen, I can't, because only Fe2O3 is allowed on the left-hand side. So I have to add a whole another set of Fe2O3. So now I have 1, 2, 3, 4, 5, 6 atoms of oxygen total on the left-hand side. So I need to add another set of O2. So now I have 1, 2, 3, 4, 5, 6 atoms of oxygen. So my oxygens are considered to be balanced because they're the same number of atoms on both sides of the arrow. But now I need to double check my irons, because before I only had 2, and because I added another molecule, now I have 1, 2, 3, 4 Fe atoms on the left. So now I have to add 2 more atoms of Fe on the right. Now that the number of atoms of each element is the same on both sides, now I can count the number of sets to determine my coefficients, or my front numbers. So I have 1, 2 sets of Fe2O3, so 2 goes in the front. I have 1, 2, 3, 4 sets of Fe, so 4 goes in front of the Fe. And I have 1, 2, 3 sets of O2, so a 3 goes in front of the O2. Now we're going to look at how to balance using a different perspective, which is using an atom count, or doing it the math way. So we're going to use the same equation because you have a visual on the front side of your note sheet about how this would look, so you have an idea of where these numbers are coming from. So looking at the left-hand side, I see that I have 2 atoms of iron and 3 atoms of oxygen. On the right-hand side, I have Fe, and I have 2 atoms of oxygen. I know Fe is only 1 because there's no number right after the element symbol, which means that there's a secret hidden 1 there. Typically, students will get to this point and then panic because they don't know where to start. So what we're going to do is we're going to find the least common multiple. And how we're going to do that is we're going to pull the number of atoms on the reactant side, and we're going to multiply it by the number of atoms on the product side for each individual element. So for example, I have 2 atoms of iron on the reactant side, and I have 1 atom of iron on the product side. So 2 times 1 is 2. For oxygen, I have 3 atoms of oxygen on the reactant side, and I'll multiply that by the 2 atoms of oxygen I have on the product side, and that equals 6. So now what I have to do is I'm going to choose the element with the largest least common multiple. So what this means is that I'm going to be choosing oxygen because 6 is greater than 2. So I'm going to be starting my balancing process with oxygen, and my goal is to get 6 atoms of oxygen on both sides to start. So let's take a second and rewrite our atom count here. So I have my elements underneath my arrow, and this is just the numbers that I wrote down in the beginning. But now my goal is to get 6 atoms of oxygen on both sides. So 1 molecule of Fe2O3 gets me 3 atoms. So I have to determine the number that would get me 6, and that would be 2. So if I put a big 2 in the front, I can take my coefficient and multiply it by my subscript. So 2 times 3 is 6. atoms of oxygen. But because the 2 is also in front of the iron, it affects that as well. So 2 times 2 is 4 atoms of iron. On the right-hand side, 1 molecule of O2 gets me 2 atoms. But if I want to get to 6, then I have to determine how many molecules would do that, and the answer is 3. So I put a big 3 in the front, and if I take my coefficient and multiply by my subscript, 3 times 2 is 6. Our last step is to adjust the remaining elements involved in the reaction. So if I look at my atom count, I have 6 atoms of oxygen on both sides, which means oxygen is balanced. However, I have 4 atoms of iron on the left and only 1 on the right. In order to get 4, I have to think to myself, well, if 1 molecule of Fe gets me 1 atom, 4 molecules of iron must get me 4 atoms. So 4 times that secret 1 is 4. So I want you to notice that our coefficients going across are 2, 4, and 3. And on the other side, they are the same. So we just use 2 different pathways to get to the same answer. So now that you know how to do both of them, you can choose which pathway works best for you to complete the rest of your practice.